Hey, what you got there?
I have this pie and I'm just eating it. It's so delicious. Do you want any?
No, I'm good. I just saw this partially eaten circle and was trying to figure out what the relationship between the circumference and the diameter was.
Oh, really? Well, that's funny because it's actually pie.
Oh, well, how did you know that?
Well, if we measure the circumference of this pie, like so, it's actually already measured and it's 30. And then you measure across the pie, right at the diameter. That is about 10 inches. So then you can just do 30, the circumference divided by the diameter, 10, and you get about 3. And pi, 3.14, 15, etc., is really close to just 3.
How do you always know that relationship is going to be 3.14?
Well, let's try something else. How about this basketball? First, we can take a tape measure and follow one of these lines, which goes right around the basketball, to get the circumference. And that is 29 inches. Then, we can measure the diameter of the ball by doing something like this, and we get about 9 inches. Now, if we do 29 divided by 9, the circumference divided by the diameter, we wind up with 3.22, which is pretty close to 3.14 and probably wasn't exactly 3.14 because I didn't measure too accurately.
Oh, I get it. Okay, so if I measure the diameter, okay, about 16 and a half, 17. And I measure the circumference. Same thing as just putting it out. I get about 53. So if I divide 53 by 17, I get 3.11, which is really close to 3.14. But who came up with this number pi anyways? Back in the day, us Greeks found that the ratio between the diameter and the circumference was about 3 for all circles, but we weren't the only ones.
The Egyptians, Babylonians, and Indian geometers were all in a race to figure out more about this ratio as early as 1900 BC. The Indian text Shatapatha Brahma, the Hebrew Bible, and a bunch of other ancient texts all tried to approximate pi as well.
Archimedes was the first one in the geometrical period to really estimate pi rigorously. He realized that inscribing circles in regular polygons and calculating the outer and inner polygons' perimeters could be used to estimate pi. By using a 98-sided polygon, he founded pi to be somewhere around 3.14159.
Other countries jumped in on the fun around 265 AD, when China's Li Hao introduced an iterative algorithm to calculate pi in the same perspective as Archimedes. Only this time, he used a 3072 gon. He later invented a quick method of calculating pi using geometric series.
Through the classical period and the computer age, many more mathematicians from many countries worked closely with this idea of pi.
The Japanese mathematician Yasumasa Kanada and his team have set the current record of known digits of pi to be 1,241,000,000,000 decimal places.
Whoa, I'm starting to get full of pi. Let's do some more math.
Okay, well let's test out Archimedes' idea of circumscribing polygons to estimate pi. Here we have a basketball, which is a circle, and we circumscribed this square around the great circle, which is the main circle, the biggest one, in the sphere of a basketball. So if we look at that, we wound up with side lengths of 9 inches. We can calculate the perimeter of that, which would just be 4 times the number of sides, which is 4, times the sides that we have since it's a square, which is a regular polygon. That gives us 36 inches, which is our total perimeter. Now we have to divide it by the diameter of our basketball, which is 9 inches as well, and that gives us 4 inches to approximate pi. That's kind of close, but we can do even better. Now, if we have a circumscribed hexagon all around this basketball, we can get even closer to pi. Again, we can calculate our perimeter. Each side of this regular hexagon is 4.75 inches, so we can do 4.75 times 6 to get our perimeter since it's another regular polygon. That gives us 28.5 inches. Again, we need to divide it by 9, and so we get 3.16 repeating inches. Getting closer to pi, but we can do even better. Now we have an octagon that is circumscribed around this basketball. Each side of this octagon is 3.55 inches. So to calculate the perimeter, we just multiply that by 8, since again it's another regular polygon. Then we divide it by 9, our diameter of the basketball, and we get 3.155 repeating. That's even closer to pi. So if we kept circumscribing regular polygons around this basketball with more and more and more sides, our polygons are going to start looking like a circle, and our ratio between the perimeter and the diameter of our circle is going to approach pi.
Archimedes tells us we can do the same thing by inscribing polygons and finding their area. Let's shout out pi in the classroom.